Hello everyone, today let's solve the problem complete mirror, right? So this was asked done Codeforces round 566 for the division 2, right? So this is rated this one 2400. So this is literally a hard problem basically, right? So let's try to solve this. First you can just go through the question. It's just this. I'll just summarize the question so that it will be easier for us to solve the problem, right? So just give me a second, 1 second, sorry. Yep, just 1 second. We are given a tree with n vertices, right? So we are given a tree with n vertices. We have to find the root vertex, right? So first we have given a tree with n vertices. Just remember this one, right? So we are given a tree with n vertices and we have to find the root vertex such that for every distance d, this one, we have to find the root vertex, right? So we have to find the root vertex for every distance d. For every distance d from the root, all nodes at the distance d have the same degree, right? So this is what we need to find again. So given a tree with this one n vertices, we have to find the root vertex such that for every distance d, this one root vertex for such that for every distance d from the root, all the nodes at the distance d has same degree. All the nodes at the distance d have the same degree, right? So that's what we need to find here. Again, if the multiple root exists, then we have to print any one, right? So we can have the multiple outputs in that case, right? So we don't have to worry. So otherwise what we need to print? We need to print -1, right? So if we don't get the answer, then we have to print -1, right? So this is, when I read the question, you would have already thought that we can go with a DP based approach, right? So when I say DP based approach, in the sense we'll be going with the subtree sizes for the centroid along with the BFS depth, right? Breadth first, depth, breadth first search, depth, grouping to verify, degree equality for the level. So basically we will be going with DP plus BFS here mainly, right? So we can just go with the iterative this one DP along with the BFS. We can go with the recursion, but the constraints are so tight, man, I'm not gonna lie. So this will fail most of the times. So if you try to use the recursion, you have to use it wisely, then you can, or with a particular algorithm if you know. So this one I find it easy when we go with the DP along with the BFS, right? DP basically on the subtree sizes for the centroid, and BFS depth basically it groups to verify the degree equality for the level. So we'll be going with the DP plus BFS, right? So this is the question is very simple. We can solve this one, we can try to solve this one in the easy way, but the constraints are very tight here in this case. So we have to go with a certain particular algorithm, or we can just go with this one here, a DP plus BFS, right? So let's see. Let me come to the input output part here. So we have been given input. So these are the edges basically 1, 2, 3, 4, 5, 6, this one 7 nodes we have here, right? 1, 2, 3, 4, 5, 6, 7. We have been mentioned 7 already, right? N equals 7. So output that we need to get here is 3, sorry, output that we got here that we need to get here is 3 basically, right? So same goes with for this one as well. We have 6 nodes here, 1, 2, 3, 4, 5, 6, and the output that here it is not possible. When I say it is not possible, in the sense so it is not possible to find the root vertex, right? So accordingly with the criteria that they have given in the question, right? So when it is not possible, we have to return -1, right? So this is fine. Now just give me a second. Let's do one thing. Let's quickly discuss the approach, right? So we I hope the question part is completely clear, right? So approach that I said, we'll be going with the DP as well as the BFS, sorry, and we have discussed the input output part as well, right? So now let's do one thing. I'll just consider the first example, the same example for the approach, right? So let's discuss the same thing. What are the data structures we'll be using, how we'll be solving the problem, what are the things that we need to consider. So constraints are very tight here. Problem seems very easy, right? So but the constraints are very this one tight. So how can we solve these problems? Let's see the same thing in the approach along with the complexities, and then let's write the code, right? First, as usual, let's discuss the approach first. So here I have considered the same first example here, this one, right? So that they have given in the question. So we have the n equals 7, note 7, see here 1 2 3 4 5 6 7, right? So the output that we need to get here is 3. So as I've said, we'll be making use of the dynamic programming along with the this one BFS, breadth first set. So these many days we were solving the problem with the DFS, right? So whenever I think of this one basically solving the problem, I'm getting the DFS itself instead of the BFS. This is fine. Now we'll be going with the dynamic programming along with the BFS, right? So this is fine. Let's move on with the step-by-step explanation. So explanation part will be very easier. So the code, whatever we write the code, so I'll be explaining the same thing while I write the code itself for this particular problem, right? So the code will be lengthier due to this one. We need to optimize this one to the core. For this particular problem, optimization is very much necessary basically, right? Question solving it, we can solve this one without using DP and other stuff that we can do, right? So we can just go with a some graph algorithm as well, right? So this is fine, but for the optimization purpose we have to go with the DP. For the extreme optimization purpose I'm speaking, right? So we have to go with the DP. So that is the reason the code will be lengthier, right? So this is fine. Now let's go with the step-by-step explanation. First, what we'll be doing, we'll be computing the subtree sizes, right? So we'll be computing the subtree sizes and we will pick the centroid. Centroid will be quite obviously 3 for this one because we have the 7. Obviously the centroid or the center node will be 3 here, right? So we have 7, right? So nodes are 7, right? So the centroid will be 3 here. From the centroid, what we will do, we will run BFS. Why we will be running the BFS? Because we need to compute the depth of every vertex, right? For every vertex, as we are making use of the BFS, not the DFS, so we will not be going with the depth. Else this one will not be going with the depth, will be going with a level, right? So we'll be computing each level, right? So from centroid we have to run the BFS just to compute the depth of every vertex, right, at each level, and collect the vertex comma depth, right? So this is fine. So now the third point is here, we have to sort the vertices by depth. So we will be sorting the vertices by depth, and for each equal depth group, we will be checking their degrees, right? So we'll be sorting the vertices by depth, and for each equal depth group, check their degrees, right? So for the depth 0, so this one we have 3 degrees, right? All all are equal basically. For the depth 1, we will be going with a 2 4 6, right? So here in this case degrees are 2 2 and 2. So here then also all are equal, again all are equal, right? So just give me a second here, what happened to this one? So finally we have depth 2 here. So we have, for the depth 2 we have the values 157, right? For the depth 2 we have the values 157. This is fine. Degrees will be 111, and here also all are equal, right? So again, what we are doing here, we are sorting the vertices by depth, and for each equal depth we are grouping for each equal depth group we are checking their degrees, right? So here for 3 we are going with the degree 3, all are equal, right? So here for this one 2 4 6 degrees are 2 2 and 2, all are equal. For 157 it's 1 and all are equal again. This is fine. I hope this part is clear, man. Now the fourth point here is, since every depth level has equal degrees, we will choose 3 as answer, right? Since every depth level has equal degrees, we will be choosing 3 as answer, right? So here you can clearly see why this is not working. Yeah, for every depth level all are equal here, right? So this is fine. Just give me a second. For every depth level has equal degrees, right? 1 1 1 2 2 2, and the third one is the first one itself was only 3. Since every depth level has equal degrees, what we will choose? We will choose 3 as answer, right? 3. So centroid is 3. We have to find the this one root vertex, I believe. Yeah, we have to find the root vertex basically, right? So condition is for every distance d from the root, all nodes at the distance d have the same degree. So we have to find the root vertex, right? So we will be find this one root vertex, will be declaring this one as 3, right? Since every depth level has equal degrees. So this is the approach that we'll be going with. Simple, right? So this seems simple. Implementing this one without DP is also simple, man, I'm not gonna lie. But when you are making use of the DP and when you are calculating this one centroid, and then when you have to go with the BFS level by level, the code becomes lengthier, right? So we will be going step by step. I'll be explaining the code also step by step, not to worry. The code seems lengthier, but it's easier to solve when we go step by step, right? So now we are done with the approach part. So here the output that we got here is 3, which is equivalent to the output that they have mentioned for the example 1 within the question, right? As we are completely familiar with the approach, now let's quickly discuss the complexities part. So what will be the time complexity and the space complexity? So the time complexity, as I have shown you, the time complexity would lead to big of n log n, right? So why it will be n log n? So first of all, let me tell you one thing. So in the worst case, first thing is it will be big of n to compute the subtree sizes. So we will be going with we have to compute the subtree sizes, right? So it will be big of n, right? So and we are going with the BFS, it will be big of n again, right? So as we are as we will be performing BFS, or accordingly with the approach we had made use of the BFS, right? So it will be big of n. Also we will be going with a sorting. This one sorting is necessary here, right? So sorting is necessary. Also we will be going with a sorting because we will be sorting the nodes by depth basically, and whenever we make use of the sorting becomes the dominant factor. So overall time complexity would lead to pico of n log n here. This is fine. So overall time complexity would be pico of n. So what will be the space complexity here? Space complexity would be pico of n. Why it will be pico of n? Because we'll be going with the adjacency lists and arrays, right? Arrays, whether it may be DP size, DP depth, DO par arrays, some of the arrays will be making use of. So that you will come to know within the code. So overall space complexity would lead to big of n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n log n and big of n respectively, right? So now as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code. Now let's start writing the code. I'll just come to the compiler here. So this one will be making use of the this one fast input and output. So I'll just import the input output package here. So this is fine. Now let's import the utility package as well, because we'll be making use of the different utilities as well. So this is fine. Now let me go with the class. So I'll just go with the class main here. So you can just give any name. I'll just give the class name main. Just give any name that's relevant to the question mark. This is fine. Now first let's go with a large upper bound for the arrays, right? So accordingly with the constraint that they have given. So I'll just go with static here, final. So this one will be int. So this is for the upper bound, right? So this is large upper bound for the arrays basically. So this will be 5 times 0, this one 5. So this is fine. Now we have to go with the adjacency list for the graph based on the question. So this we know. So I'll just go with array list. So let me pass integer. This is fine. G. So this one will be new array list. So let me pass here n. This is fine. Next thing is let's go with the DP size, right? So DP size in the sense size of the sub tree that is rooted at u, right? For this is for the centroid computation, right? So DP size, this one is for the centroid computation. Again, DP size is nothing but the size of the sub tree that is rooted at u. So I'll just go with the static here. Static, this will be int. So this will be DP size. This one will be new int of n, right? So this is fine. Next let's go with a DP depth. So I'll just go with static here. This one will be int DP. This one will be depth. So this one will be new int of n. This is fine. Next, let's go with the degree of the vertex, meaning we'll be going with the du in the sense this is nothing but the degree of the vertex u, nothing but it consists of the number of neighbors, right? So again, let me go with static here. Again, let me go with int. So this is array, so this one will be du. Again, new int of what? Again, same thing, n. So let me copy the same thing and make the necessary changes. So I'll just explain. Just give me a second here. Now this time we'll be going with a visited in the sense to avoid the duplicate length, right? So we'll be making use of the this one, visited. So we will be marking that one as visited basically to avoid the duplication. So I'll just go with visited. So this is fine. This remains same. This also remains same, and this is fine. Now let's go with this one, number of nodes, right? So we have to initialize number of nodes, also the centroid candidate, right? So these two things. So let's initialize that one. Now let me go with static here, int n, also min centroid here. Let me assign this one to the -1. This is fine. Let me go with min balance here. So this one, let me pass here integer dot maximum value, right? So I'll just go with max underscore value. So this is fine. Now let's go with a pair. When I say pair, this is vertex id and the depth. So I'll just go with static here. So this one will be class, so this one will be p. So within the this one, what do we call, one second, did I miss anything? Within the flower bracket, so we will be going with the id. We need id dependency dp. I'll just go with, so let me give semicolon here. So we need p. Within this one, what are the parameters? So this will be I, as well as d also we need. This is fine. Now I'll just go with id here, that is equivalent to I. Also let me mention one thing, dp, let me assign this one to the d, right? So we are done with this part, right? So this is fine. This is nothing but we are going with a pair, vertex id as well as the depth, right? So dependency or the depth here, this one dp, you can call anything. So this one will be basically pair, vertex id and the depth, right? So this is fine. Now one more thing, so we need the array to store the nodes with the depth, right? So we will be performing the BFS. So as I've said, we'll be going with the BFS, or we have to perform BFS. For that we need the array, right, to store the nodes with a graph. So for that, let's assign the array again. So I'll just come here, p, so this one will be b equals new p of, so let me pass n here. This is fine. Next, let's go with the count of nodes that is stored in the b. So I'll just go with the static here. So this one int, let me go with cnt or the count here. This is fine. Next step, we have to compute the subtree sizes and the centroid using iterative post order. So I'll not explain what is post order and all. So we have solved n number of problems. I have explained that this one continuously. So not continuously, basically I had stressed on that topic while solving this one, pre-order, post-order and in order, right? So these we have to know. I had stressed on that multiple times. You can just go through that playlist where I have explained and where we have solved n number of problems on post-order, this one as well in the LeetCode. So that you can just check and you can come back here, right? So we will be going with the compute subtree sizes and centroid using the iterative post-order here. Nothing but stack follows the order, follows this one, stack, order and compute, right? So that's what we'll be doing here. So I'll be going with here static. So this one, let me give void, the method name I'll give here compute subtree dp. So this is fine. Let me pass the this one, what do we call, parameter root here. So first let's go with the parent array. So this one will be int parent. So this one new int of initialization itself is giving the big headache basically. So let's go with the nodes in the this one visitation order. when I say visitation order, so I'll just go with order here. So this one will be new int, let me pass n. This is fine. Now let's do one thing. We have to get the index in order as well. Sorry, let's do one thing. We have to go with the index and order. So let me initialize k to 0. This one also we need to do, man, I forgot. Now let's do one thing. Let's go with the stack for the iterative DFS, right? So let me make use of the DQ instead of the custom stack, right? So let me go with the DQ instead. So this one will be integer, and I'll just go with the st. This one will be new array DQ. This is fine now. Now let's do one thing. Let's start from the root, right? I'll just go with st dot, let me go with push of root. So this is fine as well. Now let's initialize the parents to 0. So I'll just go with arrays dot fill. This one will be par comma 0. We are just initializing the parents to the 0, right? So now after initializing the parents 0, we have to mark the root's parent as -1, right? So this is one this thing special condition, right? So I'll just go with parent of root here. So this one, let's mark this one as -1. Now let's write the simple while loop. So I'll just go with this one. We are going with the iterative DP here. So this one will be st dot is empty, right? So operation the DQ provides basically. This is fine. We are going with the stack, right? So we have to pop node first. So for that one, I'll just be going with int u equals st dot pop. So let's make use of the pop operation for that. So now we have to record the visit order as well, meaning so this is pre-orderish, right? So this is pre-orderish. So I can just go with order. So this one k plus plus. So let me assign this one to the u. Now let's go with a simple for loop. I'll just go with for here int v this one g of u. This is fine. So within the for loop, so if the neighbor isn't the parent, then we have to set the parent and we have to push the child for traversal. This is what we need to do within the for loop. So let's try to this one articulate the same thing in the form of code, or implement same thing in the form of code. First, if neighbor isn't the parent, then how can we write this one? If v not equal to parent of u, then we have to set the parent, meaning parent of v, we have to assign this one to the u. Simple. Next, we have to push the child for traversal, meaning st dot here push of what we have to push, v, right? So we have to push the child here is v. We have to push the child for traversal. This is fine. We are done with this part, man. Let me come out of this one entirely. Now what we need to do, we have to process the nodes in reverse order to compute the subtree sizes. Again, this is also in the post order, right? So let me go with for loop here. This one int I equals n minus 1, reverse iteration, right? I greater than or equal to 0, I minus. So within this for loop, so let me assign here u equals order of I. So this is nothing but the current node. Then we have to count itself. Then we have to consider count itself, right? So we will be going with dp size here of u. This one equals 1, right? So this is fine. Next, we will be going with the int max, or I'll just consider mx here. I really don't want to type, man. Big variables name. I'll just give mx here. This one 0. So this is nothing but to track the maximum child subtree size. So that we have to do, right? So I had stressed the same statement during the approach, right? So this is fine. Now let's go with the iteration part again. One more for loop here, and v nothing but the child. This one of graph. This one u. Now within the for loop, what we need to do? First, we have to consider the again same thing, child node, right? So we will be going with v. So let me if I write this one again, instead we have to consider here dp of cell. Let me type this one, man. This is fine. The same thing here, whatever we have written, right? So the same thing, but here parent, we are not considering the parent one. We are going with the dp size of u, right? So u and v basically. So let me type instead. So if v not equal to parent of u, then what we will do, within the for loop we have to add the child subtree size, right? So I'll just go with dp size here. Dp size of u equals dp size of u plus v, right? So this will be dp size v. So this is fine. Next, let me write the simple if condition to update the max child size. Just give me a second here. So I'll just go with here. Let me write the simple if condition here just to update the max child size, right? So I'll just go with dp size of v, nothing but the child. So this one, if it is greater than max, then what we need to do, I'll just set this one max to dp size of v. Simple, right? So we are done with this part, man. Let me come out of this one entirely. Now we have to go with the largest component if u is removed, right? So including the parent side, right? So that one we have to write it in the form of code. Also we have to update this one centroid, right? So first we have to calculate the centroid accordingly with the approach. So also we have to update the centroid if the balance is improved, right? So for that, let's write the if condition. Before that, let's go with the largest component if u is removed, right? So that one I'll just go with mx equals math.max math.max of mx comma n minus dp size of u, right? So this one will be dp size of u. So let me write the simple if condition here. If max is less than min balance, so then what we will do, we have to update the centroid if the balance is improved. So let me go with min balance, so equals max also min centroid. So let me assign this one to the u. This is fine. So let me come out of this one entirely, man. Now let's do one thing. We have to go with the BFS based depth computation for the from given root basically. So we have to perform, we will be performing the BFS here mainly, right? So accordingly with the approach as I've said. So again I'm stressing on this, we'll be going with a BFS based depth computation from given root. So this one I have explained, right? So let me go with here static. So this one will be void. So this one will be void. Let me name the method compute depth. So here again we'll be making use of the dp, so I'll just go with the dp. So this one will be int root. So root is the parameter. So first let's initialize the depths to very small. This is still unvisited, right? So let's initialize the depths to very small initially. So I'll just go with arrays dot fill here. So let me pass dp depth. This is fine. Let me go with integer dot, so this one will be min underscore value. So this is fine. Now after doing this, let's go with the parent tracker for the BFS, right? So I'll just go with the int parent equals new int of what we call n plus 1. This is fine, man. Now let's go with the this one. Let's fill this one with arrays dot fill. Initially let's go with the, let me pass parent as well as the minus 1. Minus 1, why minus 1 here? Minus 1 meaning means that it is unvisited, right? So initially it will be unvisited itself. So minus 1 meaning unvisited. Don't get confused here. So next we have to go with the queue for BFS. So again, so I'll go with the DQ, right? Instead of the custom queue, I'll be going with the DQ. Don't get confused here. So this one will be integer. This is fine. Queue, let me assign this one to new array DQ. So this is fine as well. Now let me go with the DP depth here. This one of root, let me assign this one to 0. So depth of the root is 0 initially. Then we have to mark the route visited with the parent 0, nothing but it has to be distinct, and also we have to enqueue the route and reset the count of a b. This is what we have to do initially. So these many steps, man. So let me write this one quickly. Parent of, so this one root, this one equals 0. This is fine. So we have successfully marked the route visited with the parent 0. Next, let's enqueue the route, meaning I'll just go with q dot add. Enqueuing means adding. We have successfully enqueued the route. Next we have to reset the count of a b, meaning count equals here. Let me assign this one to the 0. This is fine. After doing this successfully, let me go, let's perform the BFS here. So I'll just go with while q is not empty, basically dot is empty. We have already used this one, right? So this is fine. So within the while condition, so let's go with the dq. So here in this case u equals q dot poll. This is fine. dq. The next part would be p count. So this one equals new p of u comma dp depth. So this is also fine. Let's pass u here, right? So we have to store node comma depth on array, right? So that is nothing but 1 base. So let me go with for loop here. This one int v g of u. This is also fine. So within the for loop, what we will be doing, if parent of v, so this one, if it is equal to -1, then if the neighbor is unvisited, then we have to mark the parent, meaning parent of v. Let's assign this one to the u. Then we have successfully marked the parent within the if condition. Then we have to set the depth and enqueue child. Let's set the depth here. dp depth of v. Let me assign this one to the dp depth of u plus 1, and finally we have to enqueue the child, nothing but q dot add of v. So we are done with this part. Basically, let me come out of this one entirely. Now we are left with, what do we call, 2 more methods before moving on with the main method, basically. So what are the 2 methods that we are left with? Basically we have to go with the check as well as the this one, chain linear dp. So we have to go with the check, meaning, so we have to check the candidate root x, meaning we have to compute the depth, sort by depth, and ensure nodes at the same depth that have equal degrees, right? So that's what we need to do. Let's go with the check method here. Let me write this one quickly. Static void, let me go with check here. This is fine. So let me pass x here. This is fine. Go with throws exception. So within this method, first let's fill, right? So I'll just go with compute depth dp. This method let's make use of here, right? So let me pass x here. This is fine. Now as I've said, we'll be sorting. Let's go with arrays dot sort here. What is short, man? This is fine. Arrays dot sort here. b comma 1 count plus 1. So this one p comma q. This is fine. Q dot. So this is also fine, man. Now let's go with a simple for loop here. This one will be for and I equals to I less than or equal to count, and let me increment I, nothing but I plus plus. So within the for loop, let's go with a simple if condition here. If p of I dot depth, so this one, if it is equivalent to b of I minus 1, also du, this one within the array b of I dot id. So we have already made use of the id here. Id, if it is not equal to du of this one, p of I minus 1, this is also fine, dot id, then what we need to do, so then candidate x fails. Basically we don't have to return anything, we just we will return to caller, meaning we don't have to return any output, no output, we'll just return to caller basically, right? So this is fine, return. Let me come out of this one entirely. So if all the depth groups have equal degrees, then we have to print x and exit immediately, meaning I'll just go with print writer here. So this one has to be print writer. Let me consider output here. This one will be new print writer. So new buffered writer. So of new this one will be output stream writer, right? So we are going with output, but output stream writer system dot out. So this is fine. Now let's go with the out dot let me give here println of, let me pass x here. This is fine. Now let me go with out dot flush here. This is fine. We can make use of either flush or close, right? So finally we have to terminate the program after printing the valid route, right? So this one, let me go with system dot exit of 0. We are just terminating the program after printing the valid route. This is fine. So let me come out of this one entirely. Now we are done with the check method. So next let's go with the chain linear dp method. So this is nothing but the helper method that walks along the branch, that is starting from the start, basically start, and also it ensures the branch is a pure chain, right? Pure chain meaning no node with a degree greater than or equal to 3 or the branching. So it ensures this part, and also we have to measure the length, right? So we have to measure its length in nodes, and if the length is not this one tried before the calls, we have to check on the leaf endpoint. So these things we will be doing within the chain linear dp, right? So let's try to understand the same here, or let's try to implement the same thing here. So this one will be boolean chain linear dp. So this one, let me pass start here, this one int, let me get parent here. This is fine. Let me go with throws exception. So now within this chain linear dp method, so first let's go with the u, p as well as the length. Nothing but u is nothing but the current node. Let's initialize u current node, and let's initialize the previous node p, and also let's initialize the chain length len, right? So I'll just go with int u equals start. So this is fine. P equals parent. This is fine. Len equals 0. Now let's go with the OK, which is of the type boolean, and let me set this one to initially true, boolean value true. So this is fine. Now let's go with the while loop here. While true, yeah, while of true, then it has to be true every time. So I have made use of the while loop here. So within the while loop, so let's consider node with a degree greater than or equal to 3, means branch is not the simple chain, right? So meaning branch is not the simple chain. So how can I write this one in the form of code? If g of u, so this one dot size, if it is greater than or equal to 3, then let me set the OK to false here. This is also fine. Also let me break this one. We have to break. So if the node with the degree greater than or equal to 3 exists, meaning a branch is not the simple chain in that case. Then we have to break out from there, right? So that's what we have done here. This is fine. Now this is fine. Now let's include the particular node. So I'll just go with len plus plus here. So also we have to go with the next node to go to, right? So in that case I'll just consider which is of the type integer, next equals -1 initially. So this is fine. Also we have to count of the we need to go with the count of forward children as well, right? So including p. So I'll just initialize children here. In this case this would be 0. This is fine, man. So let's go with the for loop here. This one int w g of u. This is fine. So within this for loop, so we have to consider the neighbor that isn't previous node. So this one will be if w not equal to p, then within the if condition let's increment the children, as well as if children greater than 1, then let me set the OK to boolean value true, sorry, false. We have to set this one, right? So we have to set this one to false. Also we need to break, right? So we need to break. So we have to fork if it doesn't form a chain, if it is not a chain basically, right? So we have done that one. Let me come out of this one entirely. Now let me assign the next to w, right? So meaning we have to go to the next candidate, right? So we are just assigning the next to w. This is fine. Let me come out of this one entirely now. So now we are left with certain things. We have to stop if it is not a chain, meaning if not of okay, then we have to break from here. If we have reached the leaf endpoint, then also we have to break, because no further forward neighbor exists, right? So in that case also we have to break. So this one I can write in this way: if children equals 0, then we have to break. This is fine. Now let's move forward and chain, meaning let me assign p to u. Also let's go with the advanced current node, in the sense let's give here u equals next. I hope this is fine, man. So let me come out of this one now. Now we are left with certain steps, meaning if the valid chain, if it is a valid chain and this length hasn't been tried, then we have to test the leaf as candidate root and mark that particular length that we have tried, so we don't duplicate that particular thing later, right? So and we have to set that we have to return that one true, meaning contributed, meaning we have tested that contributed this one, sorry, we have tested that particular candidate. Else if we didn't contribute, then we have to go with the new candidate and we have to return false. That's what we need to we are left with basically. Let's start with if the chain is valid and this hasn't been tried yet. So for that, let's write the simple if condition here. Okay, visited of length, this one, if it is equivalent to 0, then within this if condition that we have to go with a test leaf as candidate root, meaning u is the leaf endpoint here and we have to go with a test leaf as candidate root. So this one will be check of u, right? So this is fine, man. And next thing is let's go with a visited of length. So let me assign this one to 1. Finally we need to return true. This is fine. Else we have to return false. So this one will be false, right? So this is fine. We are done with this part, right? So we are done with this part. Now we are left with the main method. So this is also huge, man. This one also I have to type now. This is fine. Now let me go with main here. Let me delete this one. Let me include here throws exception, or else we might end up with a error basically. So this is fine. Now let's do one thing. First input output part, let me go with a buffered reader here. I've already made use of the, this one print writer, so no worries. br equals new buffered reader new input stream reader this one, system dot n. This is fine. This is for the fast input, and let's go with the fast output as well, nothing but the print writer here. So this one, print writer. So let me go with out here, this one will be fine. New print writer, new buffered writer, new output stream writer. Oh, so this one I have to give capital W here. Somewhere I have made use of this one here also. Let me make this one capital W. This one I would have got there. This is fine. Output, this has to be output stream writer. Again here also I have made, this is fine, man. Has to be output stream writer. Yep, stream writer of system.out, right? So this one, let me give system.out. So this is fine. This is related to the input output, same thing. So first, accordingly with the input what we have here, this one n we have here, right? So let me go with n equals, so this is of the type integer, so I'll just go with integer dot %. So this one will be buffered reader dot read line, and also let's go with the trim, right? So we have to trim the white spaces, so let's go with the trim here. So this is fine. Now let's go with the for loop. So why we have to go with the for loop here? We have to initialize the adjacency list, right, for 1 to n. So let's go with a simple for loop here. This one will be int I equals 1, I less than or equal to n, I plus plus. So this one will be g of I. So let me assign this one to the new. I'll just go with the array list here. So this is fine. And now let me go with one more for loop here. Int I equals 1, I less than n, I plus plus. This is also fine. Now within this for loop, what shall we do? First let's initialize the string, meaning we have to read the edge line as raw string, right? So I'll just go with the string here, s equals buffered reader dot read line. Fine. Next let me go with int sp equals s dot I'll just make use of index of here. So we need space, let me leave space here. So we are just splitting on the first space here. So this is faster than split. Instead of making use of the split, I have made use of the index of here, right? So s equals br dot read line, previous line whatever I have written. What we are doing there, we are just reading the edge line as this one, raw string, right? Accordingly with the input, you can see that one. So this is fine. Now we have to pass u and we have to pass v, right? So let me consider here x equals integer dot parse int here. So let me make use of the substring here, substring. So let me pass 0 comma sp. This is fine. Let me copy the same thing and make the necessary changes for passing the v as well. And I'll just go with a variable y here instead of x, and also instead of 0 to sp, I'll just go with sp plus 1 for this. Now we have successfully passed u and v. Now we are left with certain things, meaning we have to add the edge from x to y, we have to add the edge from y to x, also we have to update the degrees. These three things we have to do. So let's this one, add the edge x to y. So this one will be g of x dot add of this one y, and g of y, so this one dot add of basically x. Now we have to update the degrees, meaning du of x plus plus, this is fine, and du of this one y plus plus. This is also fine. We are just updating the degrees one. Now this is fine. Let me come out of this one entirely. Now what we need to do, we have to compute the centroid using the subtree dp. right? That is starting from the node 1. For that we have already written the method compute subtree dp, right? So here somewhere, just give me a second here, this chain linear dp, check this is fine. Before this one, yeah, this one, compute not compute depth dp, compute subtree dp basically, right? So this one, let me come here, the first one. So let me come here, let me paste it over here. What we are doing, we are computing the we have to compute the centroid using the subtree dp, right? That is starting from the node 1. So here let me pass 1, right? Basically we are performing the dp on the trees, right? So then we are performing the this one bfs along with it, right? So this is the idea basically, if you observe, right? So that's what I this one what do we call, I explained during the approach. So the code is lengthier because we are performing many calculations accordingly with the constraints are tight, so we are going with many other things as well. So main thing here is dp and the bfs, right? So this is fine. Now after computing the centroid, then we have to test the centroid as the candidate root, right? For that one we have written check already. So here somewhere check, yeah, this one. Let me copy this method here. So this one I'll just come here check of, let me pass here mun centroid, this is fine. Now let's do one thing, we have to set the limit just to try at most 2 chain branches, right? So I'll just go with initially, let me assign this one to 0. Let's go with the iteration part here. So this one v of this one g of min centroid, then what we need to do within the for loop. So let's go with the if condition. So we have to try or we have to go with, so how can I say this, we have to try only up to 2 distinct chain lengths, right? So here I'll just go with if this one used, if it is equivalent to the value 2, then we have to break, right? So this is fine. Now we are left with 2 more steps actually. We have to attempt to chain check for the particular branch, right? So for that one we have written the helper method chain linear dp. Again we have to attempt chain check for this particular branch, right? So for that one we have written chain linear dp method already. So let me go with boolean here. So let me go with contributed here. So I'll just come here, let me go with chain linear dp, this one, and let me paste it over here, right? So chain linear dp, this one v comma, let me pass mun centroid, this is fine. Yep. Now let's go with a simple if condition here. We have to count only if we have tried a new chain length, right? So if of contributed, then only we have to increment the used, right? So I can just write it on this way, if, let me pass contributed here, then only we have to increment the used, meaning if we have to count only if we have tried a new chain length. So now we are done with the coding part, finally, right? So let me come out of this one basically from the for loop. So now if we didn't exit earlier with a valid route, then we have to print -1 accordingly with the question, and then we have to flush the output. These 2 things are remaining, so let's do that quickly. So I'll just go with the out println here. So we have to print -1 within the string, right? So let me give -1. Also we have to flush the output, so for that one I'll just go with out dot flush. So this one, flush out, this is fine. Now we are done with the coding part, right? So before checking the code with different inputs, so this was code was really lengthy, man, 158 lines of code. So this is fine. Now let's do one thing, let's quickly before checking the code with the different inputs, let me copy paste the signature starter template. Just give me a second here. So let me come here and paste this one, man. This is fine. Yep. Yeah, now this is fine. I'll just come to the question. Let me copy this one. Output that we need to get here as 3. Let's check. So we have oh yeah, I have given extra comma here, line number 30. where is this? This is depth, right? Dependency of the depth. This is fine. Now let me run this one. Oh, we are left with one error saying unchecked conversion. So this is warning or error, man? This is fine. This is warning, right? So this we can ignore. Now let's go with this line number 100, bad operand types for the binary operator, double equals. So line number 100, let me come to the line number 100 here. So this is within the check, right? So what is wrong here? Just give me a second here. So we are going with this one, check, right? So this one, if b of I dot depth I have given, this one has to be the previous value we are considering, right? So it is equivalent to b of I minus 1 dot dep, it has to be. So this is fine. Now let me run this one again. Yeah, now this error is gone. We are getting the output 3, correct output, right? So we are getting the output 3. So let's ignore this one. What do we call? Warning. Warning doesn't matter. For the second one, we have to get the output -1. Let's check. So if I run this one, we are getting the -1. So our this one code works absolutely correct, right? So these are some of the things that we have that we are using for the optimization. Basically the checking part, chain linear DP, right? So this one compute depth DP. So this one, if we would have made use of the DFS, recursive DFS, it would have been better, but I was repeatedly getting this one clearly. I couldn't optimize basically with the recursion, so I opted this one BFS along with the stack basically, right? So now this works absolutely correct. Let me do one thing. Let me copy this one. We have went with a pure DP on the trees along with the BFS, right? So let me copy this entirely. Let me come here. Let me submit. Just give me a second. They have given the diagram, man. You can just try to understand this one, right? So first and the second example, you can just try to go through this one diagram. Basically you'll understand this one clear. So this is easy to understand, right? So implementation is difficult, I'm not gonna lie. For this particular problem, implementation is quite difficult. So this is fine. Let me copy this one and let me hit the submit button. I hope this works for all the test cases, man. Let's see. This is literally the hard question basically. Yeah, you can clearly see here on the toast. In the toast we are getting accepted, right? So the verdict that we got here is accepted as well. So we have went with again we have went with the some of the helper methods, basically compute subtree DP, we have to basically, and we are going with the compute depth, this one DP. So this one we have to calculate the depth as well, compute the depth as well, and we are making use of the check for the checking purpose, and we are going with the chain linear DP method as well. This is also required. So these are the some of the methods, helper methods we are making use of, right? So yeah, again we are making use of compute subtree DP, this one check, and this one chain linear DP, right? So whatever the helper methods that we have written. So this is pure DP. We are performing DP only on the trees, and mainly we are going with a BFS here, right? So breadth first search to solve this particular problem, right? So I hope the solution part is completely clear, man, along with the approach and the complexities, right? For now, this is it. Thanks for watching, guys.